Okay, so today let's do some review before we start section 4.5. Let's look at the graph of the natural log of e. I'd like to show you, of the natural log and of e. So for example, if we have to graph f of x is equal to e to the x, e is an irrational number, but we can still simply graph it. The graph will still have a y-intercept at 0, 1. We'll take off to infinity as x goes to infinity, and we'll approach 0 as x goes to negative infinity. So the horizontal asymptote still stays at y equals 0. We still have the y-intercept. The domain stays as all real numbers. The range goes from 0, but not including because of the asymptote, and goes to infinity. It is a one-to-one function. Now the question is, how do we label this if we're not using a calculator? The answer is it's quite easy, actually. If x is 1, then I would put an e to the first power, which is simply e. If x is 2, then we would substitute in 2 for x. So our ordered pair would be 2, e squared. Below, when x is negative 1, it would become 1 over e, because e to the negative 1 is the same thing as 1 over e. We can also label the point negative 2, and then this would become 1 over e squared by the same logic. Okay. So this is how you graph e to the x without a calculator. Now remember, its inverse would have to be symmetric just as any other inverse would be, with a line y equals x, which is that 45-degree line. Okay. So its inverse, we would flip-flop the points, and remember, then this would become an x-intercept of 1, 0. We would take off to infinity as x goes to infinity. But now, instead of having a horizontal asymptote, by flip-flopping the points, we get a vertical asymptote. And that vertical asymptote has the equation x equals 0. So the graph would approach like this. And now to label it, we'll just flip-flop the points. So when x is e, the function, the inverse function, is equal to 1. If we have e squared, then it's 2. At 1 over e, there must be the point negative 1. At 1 over e squared, we must have the point that has negative 2 involved. Okay. So this is its inverse function, and the inverse function is written as the natural log of x. All right, let's do 10 to the x. Okay. If we were to graph f of x equal 10 to the x, again we will have the y-intercept of 0, 1. It will take off to infinity as x goes to infinity, and we'll approach 0 as x goes to negative infinity. So we can draw in the horizontal asymptote of y equals 0. And now we simply have to label some points. Okay. So if x is 1, then we would get 10 to the first power, which is just 10. If x is 2, then we would get 10 squared, which is the same thing as 2, 100. negative 1, we would get 1/10, because 10 to the negative 1 is equal to 1 over 10. At negative 2, we would have 1 over 100 by the same logic. Again, the domain stays the same. It goes from negative infinity to infinity. The range starts at 0, but will not include 0 because of the asymptote, and goes to infinity. This is a one-to-one function. And so its inverse will also be a function. And to graph its inverse, remember it must be symmetric about the line y equals x. And now we can draw its inverse over here, putting in now the vertical asymptote, like so. The equation of this asymptote is the line x is equal to 0, because it's vertical. So we would get the point 1, 0. We also would have the point 10, 1. We'd also have the point 100, 2. Down here, we'd have 1/10, negative 1. And here, 1 over 100, negative 2. This is the graph of its inverse, f inverse of x, and that is written as the log of x. Now remember, when when we don't see a subscript here, it is understood to be base 10. So if you want to write base 10 in there to remind yourself, that's fine. It's not incorrect. And let's talk about the inverse then. Now the domain. The lowest value of x we can pick up is 0, but not including 0, and goes to infinity, while the the range now goes from negative infinity all the way up to positive infinity. This is also a one-to-one function. I've posted some worksheets for you to work on this and to answer some other questions, so I highly recommend that you get those done. Okay? So, now let's start the lecture for section 4.5 with that intro in mind. In section 4.5, we talk about the rules of logarithms. So we know this. We know that if we're given f of x is an exponential function, a to the x, and its inverse, it's written as the log base a of x. So these two functions we know are inverses of one another. And since they're inverses, we can look at what happens when we compose them. So if I take f, and into it I put f inverse of x, well then by definition of inverses, well first let's see what it looks like. In this case, that would be a, and f inverse is the log base a of x. So if I were to compose those two, then we know by definition of inverses that when you compose them, that must be x. That is, it will undo each other. And we could do it the other way as well. We could say, let's take f inverse, and into it I want to put f of x. So the way that would look is I would take the log base a, and into it I would put a to the x, and by definition then, that must be equal to just x. So let's see if we can use these to do some simplification. So for example, let's simplify the log base 5 of 5 that's raised to the power 2x minus 1. So what we'll notice then is that the log base is the same as the base in what they call the argument. These two are the same. So I'm in this situation, log base a of a to some power, and the answer will just be the power. So in this case, our power is 2x minus 1. And that's how this expression would simplify. Now, if we had e to the natural log of 2x, now we're in this situation where I have a raised to the log of the same base. So in this case, a is e, and the logarithm that associates with e is the natural log. So these two are the same. So by definitions of inverses, the answer has to be this argument. So this will just be equal to 2x. So this will take a little bit of practice in getting used to seeing this notation, but once our eyes become accustomed and our brain understands that these are undoing each other, they become quite simple problems. Now, we also have three big properties that associate with logarithms. So here's our big three properties. I recommend putting these on flashcards until you've internalized them. Number one, if we're taking the log base a of some product m times n, then we have the ability to split that up into two separate logarithms. We could take the log base a of m and then add it to the log base a of n. Number two, if we have the log base a of a division, m divided by n, then we can take the log base a of m, which is the entire numerator, and subtract it from the log base a of n, which is the entire denominator. Let's say we have the log base a of m raised to the n. What this rule allows us to do is take this power and bring it outside and multiply now by just the log base a of m. So let's do some examples in how this can be helpful to us. Let's say we have the log base 3 of 18, and we're subtracting the log base 3 of 2. In this case, here we have a log of the same base of two things being subtracted. So we could recombine them and write this as the log base 3 of the first one divided by the second one. Now inside of here, I can simplify. So this will be the log base 3 of 9. And now we can evaluate this. We know that this is the log base 3 of 9, but remember 9 is 3 squared. And now by rules of inverses, these two match, and so our answer must be the exponent. Let's try another one. So let's say we have the natural log of x to the fifth, and we subtract the natural log of x squared. Again, we have a subtraction, so we can write that as a single logarithm. This time, we'll take x to the fifth, and it has to be divided by x squared. Now there's simplification that can occur inside of here. This is the natural log then of x cubed. And now we have, we are in the third case where x is cubed, so I can take this power and move it outside by rule 3. So this expression is equal to 3 times the natural log of now just x. Let's think about this. What about the log of the square root of 5? And if we were asked to simplify this? Well, another way that we could write this is the square root of 5 is 5 to the 1/2 power. Just rewriting the radical in exponential form. And now we can use the power rule just as we did above. And we can move this power outside of the logarithm. And now we have 1/2 the log of 5. So we were able to get rid of that square root. And this will work for any power. Okay. What do I mean? I mean if we have the natural log of the square root, let's do a cube root of x. We could write this as the natural log of x to the 1/3 power by writing this exponentially. And then I can take this power and bring it outside to get 1/3 the natural log of x. Alright, let's do some other expanding. So let's say we had to expand log. For example, let's expand the log base 3 of 30x times the quantity 3x plus 4. In this case, I actually have a product. Here I'm taking 30x and multiplying it by 3x plus 4. So since this is a product, I can use our rule to expand it. That would be the log base 3 of the first, which is 30x, plus the log base 3 of the second, which is 3x plus 4. So in this way, I'm simplifying the logarithm. Now inside of here, there is no more multiplication. There's a multiplication here, but the addition is breaking that up. So our rules only apply to products. So this logarithm is as simplified as it can get. Over here, however, we have yet again another multiplication, another product, so we can split that up. So we could write this as the log base 3 of the first, which is 30, plus the the log base 3 of the second, which is x. And so with all of this now, we have expanded this logarithm. Let's look at this. If we have the log base 2 of x to the fifth, well, we can use our power rule here to simplify this. There's a power of 5 here that can come out. So this could be 5 times the log base 2 of x. We could also look at the natural log of 1 over x squared. There's a couple ways we can go about this. One thing we could do is that we could write this as the natural log of x to the negative 2, just rewriting 1 over x squared. And now we could apply the power rule and pull that outside. So this would be minus 2 times the natural log of x. Alternatively, we wouldn't have to rewrite this. What we could do is we could look at this as the quotient, as a division. Okay? And so we could use the subtraction rule that says, well, if you have a division, you take the natural log of the entire numerator and you subtract the natural log of the entire denominator. And now we need to simplify this. We have to ask ourselves about what the natural log of 1 is. Well, remember our graph. Any inverse will look like this and has the point 0, 1. So does the natural log of x. That is, when x equals 1, the natural log equals 0. So this becomes 0. Minus. And now let's simplify the power. Okay. Pulling that outside, 2 times the natural log of x. And 0 minus 2 times the natural log of x is simply negative 2 times the natural log of x. Let's do another. For example, let's say we have the natural log of x to the 4th y over 7. And we need to expand this. So if we expand this, there's nothing to simplify inside of here, and if you could, I would simplify it before expanding. So in this case, there is nothing to simplify. So this is the natural log of the entire numerator, which is x to the 4th y, minus the natural log of the entire denominator, which is 7. Now from there, we could also look at expanding further, because here is a product. Okay. I have x to the 4th and y. So I can split this logarithm up to the natural log of x to the 4th minus the natural log of y, and the natural log of 7 comes along. Lastly, excuse me, we can simplify this power. Pulling it outside, this becomes 4 times the natural log of x minus the natural log of y minus the natural log of 7. And thus we've expanded it. let's do some combining now. So let's say we have the log base 2 of x squared plus 1/2 the log base 2 of x minus 1 minus 3 times the log base 2 of x plus 3, and let's square that quantity. Okay, so there's a lot going on, and we want to write as a single log. So, following the order of operations, okay, here's one term, and here's another term. The first thing I would do is the addition, so I'm going to combine these two. Okay. Actually, let's not combine them quite yet. Let's deal with their multiplication. Okay. So we know that I could bring this up as a power, okay, and I could also bring the 3 up as a power. Let's do that first. Okay. So let's look, this would become the log base 2 of x squared plus the log base 2 of x minus 1, now to the 1/2 power, minus the log base 2 of the quantity x plus 3, which is already squared, and now we can bring the 3 up and make it cubed. Right. Let's simplify a little bit further. So we have the log base 2 of x squared, that stays the same, plus the log base 2 of x minus 1 to the 1/2, and now minus the log base 2 of the quantity x plus 6. And now we need to simplify. When we're going power to power, we need to multiply those. So now we have, now we're ready to combine these. Okay, working left to right, here's one term and here's another. These are being added together. So I can combine this as the log base 2 of now their product of x squared times the quantity x minus 1 to the 1/2. That's the single logarithm. Now we're subtracting the log base 2 of x plus 6. I'm sorry, this should be x plus 3. Sorry about that. Okay, x plus 3 to the 6th power. Now, what I have is a subtraction of 2 logs in the same base, so I can write this as one great big log, the log base 2 of the first becomes the entire numerator, x squared times x minus 1 to the 1/2, divided by, and this will become our denominator, x plus 3 to the 6th. And so in this way, we have written all of this as a single logarithm.